Okay, I guess you can now see my screen. So we're gonna talk a little bit about classical Hodge theory, and there's no other way since we have, I guess, an audience from all backgrounds. I'm gonna start very basic because there's no other way. But as time goes on, as we move along the material, we're gonna see more and more advanced topics. So you feel a little bit, you feel it's very easy at the beginning. Don't worry, it will get more interesting with time. So let's start. We always start with what is the plan of classical Hodge theory? Hodge theory has a lot of things to say about. We cannot encapsulate Hodge theory in a single topic nowadays. Although in the past, at the beginning, it was very clear what Hodge theory was. But now we can talk about a lot of things. So my goal in these 3 sessions is, sorry, 4 sessions, is to go to the very basic core of the subject, which is what is the Hodge theorem and what is the Hodge decomposition, right? So let's start very basic with, well, first we start with a differential manifold. As we all know, a differential manifold and some people call this a smooth manifold instead of differential, right? It's a topological manifold with a C infinity structure, right? So for those of you who don't know what this is, a topological manifold is a topological space M together with that is Hausdorff and locally Euclidean. Okay. What do I mean by locally Euclidean? It means that when you have a point here, then you can find an open set such that you have a homeomorphism of the open set with its image, right? And this number here is fixed for all homeomorphisms of this type you can find, and it's called the dimension of the manifold. In this case, of the topological manifold. But that's just the topological manifold. So for a manifold to be a smooth or differential or C infinity manifold, there are several names for this. You need that you have a family of charts. These things here are called charts. Such that the union of this open set gives you the whole M and more importantly for us, that the composition is C infinity as a map from Rn to Rn, okay? And sometimes, well, they ask, well, this is part of the definition, but you can always show that the following, that the collection, sorry. Is maximal. And what do we mean by maximal? It means that whenever you have a chart and you have members of the family such that this composition RC infinity, then the chart itself is in the family, right? So, of course, there are another different definitions of smooth manifolds depending on whether you ask C infinity or CK or whatever, right? Okay, and so
Olivier, it seems that there is a problem with Jaime connection.
Yes, let me. I'm trying to contact him now. Jaime, te perdimos. Sí, por favor.
It is usually good to make little breaks. I mean, during talk.
Well, but this was scheduled after 40 minutes, not after 5. He's trying to reconnect. Okay. He's back. So Jaime, now we're back.
Yeah, sorry for the technical, I don't know what happened here. Okay, so going back to our presentation. So, okay, so we have a differential manifold. Are everybody listening again? Sorry.
Yes.
Okay, so whenever we have a differential manifold, or a smooth manifold for short, as you know, we can talk about the space of the tangent space at every point, which is the space of derivations. We can talk of it that way. And then we can talk of the tangent model more in a minute of this. And so this space here, sorry, is a 2n dimensional manifold. Okay, and then a vector field is continuous map. Sorry. From the manifold to the disjoint union of the tangent space itself. So it's what we call a section of the tangent bundle. All right, and then why do we use the word bundle? Because it's a bundle, a vector bundle in the following sense. So a real vector bundle is nothing but well, I should say of rank K. It's a topological space E together with the surjective continuous map I such that if we take a point in the manifold, well, here we always start, did I say that? Yes, we start with a differential manifold, with a smooth manifold. So if we take a point, then the pre-image of that point is a k-dimensional vector space. Of course, this space should be a real vector space. And then if you take a neighborhood of P, then you have a homeomorphism between U and U times RK. This is where the rank appears as well. You can find maps which are homeomorphisms. Such that when you take the projection and compose, you get pi, where this P1 is nothing but the projection on the first factor. Right. And these maps are called local trivializations. And then the other thing we need, besides, there are three things here. You have a K vector space in the fiber, local trivializations, and we also need that when you restrict the local trivialization to one of these spaces, you have something that goes to QRK by property 2, which is of course isomorphic as vector space to RK. Then this should be a vector space isomorphism. So we say that a vector bundle is a smooth vector bundle if pi is not only continuous, but also smooth, right? Here, I didn't say anything here at the beginning, but for that, we also need that E is a manifold, right? So, our friend, the tangent space, which glued to get what I call the tangent bundle. This is indeed a vector bundle, right? Where pi is just take the point, right? So whenever you have a vector bundle, you can define sections. A section is, sorry. A section is nothing but a continuous map C that goes from M to E when you have a vector bundle. Such that when you go back by pi, you recover the point, right? What that means is that sigma p is actually in EP, right? So the picture everybody draws is the following, right? You have M here, and you have your vector bundle here. And so you have your vector bundle moving here. So this is EP, right? This is pi. So a section is one of these semi-horizontal lines there, right? So, okay. So whenever you have a vector bundle, so in this sense, I say that here above, sorry for moving the screen so fast, but there's no other way when you have an online class. But anyway, so I define a vector field as a section. So this is the rigorous definition of a section, right? Considering Tm as a vector bundle and then take the definition above. It's nothing really complicated. So when actually these things are defined here are what we call global sections, right? Because we can change the definition and there's nothing mysterious with asking for M to be the domain of the map. I could have defined a section just taking any open subset of M, right? So those are sections as well. So are sections as well. So we still ask for the following. But we can use either of them. So, but we have a special name for sections which use the domain as the whole M, and we call those global sections. So whenever you have a vector bundle, so E is a vector bundle. You can always define the dual bundle. Right. So I'm not going to say a lot about this because for that, we need to introduce transition functions. But to be really quick about this, the only thing you have to keep in mind is that when you have an element in your manifold and you consider the pre-image, I said that this is a vector space. So since we are in the world of linear algebra, and this is a word I'm going to use a lot in this course, linear algebra is very important in Hodge theory. You can consider the dual vector space associated to EP, right? And so there's a form to glue the dual vector spaces to get a new vector bundle, right? And this is done via the transition functions. I'm gonna repeat the same definitions for the complex case, so I'm not gonna stop in this part now, but we will see this again. So the point is that we can construct the vector bundle associated to, let's say, we usually the vector bundle is not only E, but also the map. But let's say, in practice, we use the word E. So whenever you have E, you can talk about the dual bundle, but you can also talk about the tensor product and the of vector bundle, etc. What I'm interested right now is the following. When you have, let's go back to differential geometry. We have the space of derivations, and you can always talk about the cotangent bundle. And for this one, you only need to take the dual of this one. And so the cotangent bundle is nothing but taking, again, the union of this one here, right? This is the space we're interested in because a section of the cotangent bundle is what we call a differential form. Actually, it's a one form, right? This is the differential forms we are used to, okay? So that's the reason I have to start really slow in this part. Okay, give me a second. Give me a second, please. Okay. Yes. So whenever you have the cotangent bundle, you can associate by linear algebra. You can take the alternating product of, locally in each point, you take these spaces, and then you can take, sorry, here. You can take the alternating product here, and then you can take the union of those, and this is the space of alternating tensors. And this one, it turns out that this is as well is also smooth vector bundle on N, right? So why did I introduce this? Because a section of this vector bundle is what is called a differential K-form. So there are several names for this. In the global case, some people, well, if you don't want to mess with notation, basically you can say that since we are in the C infinity world, some people use this notation for the global sections. Some other people use this notation. So depending when you are reading or which notes you are following, there are several ways. Of course, there is the basic, this one. But I'm gonna reserve this one because we're gonna use this later in the complex case. So some people actually use this. And in more classic books, they use things like this, right? Or just A, E. So it seems like a waste of time to say that we have different notations, but the truth is that there's no like agreement in which notation to use. And even in modern books, there are several ways to denote the same space. There are inclusive, you can use the classical in, another classical one is this one, right? Or if you want to emphasize that you are in the real world, you use this one. So I'm gonna try to stick to one, maybe to this one, and not to change it, okay? So locally, what do we mean by the word locally? That means in a smooth chart, a differential form looks like, and this is the picture we have when we start to learn these words. Is locally is just you already know. It's something like this, right? Whenever you have a differential form in this way, you can derivate, right? So whenever you look locally, again, I have to say that you can change here the M for any subset of M. So instead of taking global sections, you take sections in an open set. That's why in all these notations above, the M is always emphasized, except in this one, right? So whenever you have a local section, in this case, a differential form locally, you have the exterior, this is called the exterior derivative. And what the exterior derivative does is that when you take locally a form, you take it to the differential of the form. And the important theorem for us is that, well, there are some other properties of D, like it is linear, and you have the Leibniz rule, etc. But what is going to be important for us is that if you derivate twice, you get 0, right? And so for us, CKM is going to be the spaces close. I'm going to say what this is, K forms. or differential forms. I'm just using forms for short. What is this space? It's just the kernel of the map D from, sorry. I say that I wasn't switching between notations. It's just the kernel of this map, right? And continuing with the definition, we have the space of exact forms. That this is nothing but the image of a k minus 1 by D, okay? Okay, so this leads us to the first important definition of this course, is that you take a smooth manifold, the K DRAM cohomology group of M is by definition, and again there are several notations of what to put at the bottom of the H, but anyway, let's use this one. It's just the space of closed forms modulo exact forms, right? Nothing new there, right? Okay, this is a very important space. It's an invariant. Actually, it's a topological invariant of the manifold, and this is the starting point of Hodge theory. We're gonna improve our understanding of these groups through the days. So this is all in the real world, right? We have a smooth manifold in which you have local homomorphisms to R something, and then you have real differential forms. We're going to improve this in two ways. One is that we are going to jump a little bit later to the complex world, and then we're going to understand better through spectral sequences. We're going to understand how this group behaves. Okay, this model. So now, why do I use the word? The letter H here, because we reserve this for cohomology in general. Well, first of all, we have, I didn't say this, but you have a complex here, actually. You have zero forms, one forms, etc. So I'm not using anything new here. It's just that actually here I have the constant functions, right? This is the C infinity functions in M. So what I'm just doing is topologically is the cohomology of a complex. And the other thing coming from topology is that whenever you have the RAM cohomology groups, you can map them to the space of singular cohomology. And by singular cohomology, I mean the cohomology you take by using chains, cochains in this case, right, over M. And so I shouldn't go to the next topic without saying first a very important theorem. This is the famous RAM theorem that says that this map, this canonical map from the RAM cohomology to singular cohomology, it is actually an isomorphism, right? So we are good, right? And how do you prove this? I'm not gonna say this, but there are several proofs. You can do this directly, but I mean, you can do it. I'm not gonna prove it. Just gonna say that you can do it via integration. I mean, very basically, you can do it with just tools of differential geometry or via chips, which is the more elegant proof. I'm not gonna talk about that, but you can use whatever you want to prove it, okay? Okay, so, okay, any question? Okay, I guess, okay, I'm gonna take 1 minute more, so. And okay, I'm gonna say a little bit about this part. When we do we're gonna repeat this later, but when you use it via chips, what we have is that, actually via chips, what we have is that you have a chip actually. So when you have global sections, you have a map from the global sections of the chip to the cochains on M, and actually that's the way to prove that the RAM theorem in this case. And actually you can also prove well, via chips that actually what we are gonna need, I'm gonna talk about this later, but also you need to use the fact that when you take singular cohomology, this is the same as the cohomology of M over the constant chip of M, right? Okay, if you look at this suspiciously, don't worry, we will talk about this theorem later. But okay. So I guess it's 40 minutes, Pedro. So
sure, let's do a small break. Thank you.
okay. Ready? Okay, before continuing, I have to make an announcement because it seems like we are living like this is a very one-way lecture, because we have a space later for questions. So you have questions, remember that we have the Solid to ask questions in the chat, and that we also have in the afternoon, we have rooms for each of the courses in the morning and the early afternoon. And then you can enter there to ask specific questions about any of the lectures, okay? So if you have questions at the moment, you can write them down right now in the Zulip chat, and then we can discuss them in the afternoon, okay? So, okay. So what we were in, okay. Okay, so we have the rank homology of a smooth manifold. So now I'm gonna use more structure on the manifold. Let's take, now we have to ask it to be compact, a compact oriented Riemannian manifold, right? Of dimension n, right? Compact and oriented are new conditions. Riemannian is always possible to get a Riemannian metric on a smooth manifold, okay? So that's not something we should worry about. But the other two, yes, we should. We should require the manifold to be compact and oriented, okay? So whenever we have a Riemannian manifold like this, we have sorry. It is possible to define a linear operator called the star operator. That goes from the space of, let's change a little bit the index here, from the space of P forms to the space of N minus P forms. I'm not gonna describe it completely, but yes, I can say that locally, or I should say, using linear algebra, this is a construction actually in linear algebra. Whenever you have a space, finite dimensional vector space, what the star operator does is that when you have the wedge product of elements of the base, what it does is that you take these elements to the wedge product of the following ones, right? So actually, and this is plus minus, it depends, right? You have the signature there playing. So actually, when I say linear algebra, what that means is that the star operator comes from taking the alternating space of a vector space and does something like this, right? So you shouldn't worry about this. Just to know that there's a linear operator that goes from the space of P forms to the space of N minus P forms, where N is the dimension of the manifold we are using, right? And there are several properties of the star operator. One of them, for instance, is that we're gonna need this later, is that when you compose the star operator with itself, you get classical, it should be, let me see. It should be P I minus P, N minus P. And then, okay, this seems like a kind of artificial, but I will say in 2 lines why we are introducing this. Then we can define the delta operator, which is -1 M plus P plus 1 plus 1. Don't ask me why, but this is the reason. And then you use the star operator. And then what does this have to do with what we saw in the previous 40 minutes? Well, now I'm using the D operator, right? Remember, the star operator is on forms. So we have the stereo derivative, and again, we use the star operator. So this seems like very technical. It is actually very technical, but the reason is the following, is that the Laplacian, or what we call the Laplacian in Hodge theory, is the linear operator on the space of P forms given by delta D plus D. This is called the Laplacian. Now, for those of you who now are thinking, I already know a word Laplacian used for something else in calculus, but the reason is that when you take A0 of Rn considered as a manifold, then this Laplacian is actually the Laplacian, okay? That should be, I need a -1 here, I think. With my definition, yes. So we recover the Laplacian. Of course, this definition is more general, is for any compact oriented Riemannian manifold, and that's the important thing. So, for instance, the Laplacian commutes with the star operator by definition. And then we can define an inner product by, let me see. You take two forms. You take alpha star of beta and integrate over there, okay? So this is an inner product on AP and R, okay? Do we agree? The star product takes a P form on an N minus P form, so everything is fine. And then what else should I say about this? Okay, I should say the following. We have more properties of this. You take the inner product of the exterior derivative of a form with another form beta, and this actually should be alpha delta beta. So what this is telling us is that delta is the formal adjoint, I mean, as in linear algebra adjoint, is the adjoint of T, right? And so as a corollary, I mean, this is just a matter of notation. Nabla is self-adjoint, the Laplacian, right? What that means is that when you take the Laplacian of alpha and beta, you actually recover alpha nabla beta, okay? So the Laplacian is self-adjoint, and then with this at hand, we can show that the Laplacian is zero if and only if both D and delta are zero, okay? So what do we do next with this? Okay, classically, and this is where the word classical Hodge theory enters in the picture. What people in the 40s, 50s, and Hodge and all of them were interested is in the following. They have a differential equation like this. I mean, they wanted to solve the Laplacian equation, okay? This is historically, this is the way they got to this. Okay, this is all in the papers by Hodge. You can read them. They are not an easy read nowadays, I think, but still worth it. And then, so the question in here is, how do we solve the Laplacian equation, this differential equation? How do we approach to this, which seems like a complicated thing to do, right? I mean, and this is more general than solving the Laplacian equation just in a Euclidean space. This is we look for a solution in general, for a solution in any compact Riemannian manifold, oriented Riemannian manifold, okay? How do we solve this in general? Well, we can do some observations. If omega is a solution, then if we consider, we now use the inner product, then we consider the Laplacian omega with another form phi, this should be what? It should be alpha by phi, right? And then we can sort of solve for omega using the adjoint, right? Here is here nabla star is the formal adjoint of nabla, which we know here that is actually nabla itself. But just for the moment, let's assume it's just a joint there's that joint and we don't know anything of it. Okay. And so so what was okay. So if we have the Laplacian equation, we apply the inner product, and then we get this. Okay. And this should be true for every form in A, P, and in the space of P differential forms. Okay. So we define L of beta as the inner product of this, and this is a linear functional. Actually, this is a bounded, for those who know a little bit of functional analysis, is a linear bounded linear functional. Where on the space of P forms, such that when you take, using what I wrote above, when you take the functional of the adjoint of the Laplacian applied to phi, what you get is alpha. Okay. So we would like to find, so to find the solution of the Laplacian here above, I have to try to do something like this. And then if, as I say here, if omega is a solution, then I find this identity. So to find the identity is equivalent to find, well, not equivalent, implies that you can find a bounded linear functional that does this, right? So we take that as a definition. A weak solution of the equation nabla omega equal to alpha is a bounded linear functional on APMR. I mean, L goes from A, P, and to R, such that okay, we require what we found. Such that when you apply L to this, you get this for every C in A, P, and okay. So whenever we have, so what I just said about this above is that when omega is a solution of the Laplacian equation, then what I did above is that L defined as above is a weak solution. So what is surprising, and this is the first important thing in Hodge theory, is the converse, is that whenever you find a weak solution, you can find a complete solution or determine a solution. I'm going to state this carefully. each weak solution let's put it this way, determines an ordinary solution. Of the Laplacian equation, okay? I'm gonna put this very vaguely because we're gonna be clear about this, but this is a property, very important property that is called regularity, right, okay? So whenever you want to find the solution to the Laplacian equation in a Riemannian manifold, you can just look up weak solutions for the Laplacian equation, okay? That's the yoga, that's the, let's say the form we do it, right? Okay. But what I mean by this is that when this happens, there is a smooth form such that that weak solution we have is like this. And then how do we solve it? Okay, suppose we have the weak solution. Then what we do basically is that you take this and then you use the adjoint, right? And then this should be our L of this star, yes. And this should be, by the property of a weak solution, this should be alpha beta for every beta. Then you have this, and since the operator is bounded, etc., then you get the solution, right? Okay, so let's state this carefully. Okay, a lot of you should be asking now, why is he talking about solution of the Laplacians when he talked about the RAM cohomology before? Don't worry, we will say what is the relation perhaps at the end of this class or the next, or at the beginning of the next one, okay? We're gonna relate these two things in a very clever way, which is like the start of the interest in Hodge theory, okay? Just be a little bit patient and we will see how it pays, okay? So, okay, what it says, the regularity here. Okay, by the above, we know that it is enough to look for weak solutions. Okay, so suppose that we have a form here. And L is a weak solution. Okay, I have to say something here before I continue. Here at the top, I say, when I say determines, this word here, what I'm really trying to say is that, I mean, not because you have a weak solution. Let's go a little bit back to the weak solution definition. A weak solution is just a bounded linear functional with this property here. But that doesn't mean that the bounded linear functional is of this form, okay? That's actually the input of the regularity theorem, okay? That's the strong part of the regularity theorem, that every weak solution is actually an inner product of something, of some sort, okay? So the regularity theorem says that whenever you have a form and a weak solution, which is just a linear bundle functional with some property, suppose you have a form, a weak solution of the Laplacian equation, then there exists a differential for omega such that the linear function applied to any beta is actually the inner product of beta with that omega for every beta, a differential form as well, right? And as I showed above, in consequence, that omega gives you a solution to the Laplacian equation, right? Okay, the regularity theorem, it is a very hard theorem. I'm not gonna prove anything of it because the proof actually requires hard functional analysis, right? And by hard, I mean very hard. So you have to know a big deal of elliptic operators and stuff like that, right? Of course, you are interested in the classical part of Hodge theory. It's a proof you should know. At some point, you should study the proof. It is very classical. You can find it in books like in classical ones, like in Griffith Harris or in Warner book, which is fantastic. But in more modern treatment, you can find the proof in the first volume of Wasan book. You can find a proof of this regularity theorem, but it's not easy. Okay, so okay, once we know this, how do we relate this to the previous part of the RAM theory? Okay, so first of all, we introduce the space of harmonic P-forms is given by, and we use these spaces with H, like it's not a normal H, it's like a calligraphic H. These are the forms. Oh, okay. Let's just so that when you apply the Laplacian, you get 0. Of course, when you have the Laplacian on real in an Euclidean space, you get the usual definition for harmonic function. Okay, so there's another theorem which is a consequence of the regularity theorem. This is the Hodge decomposition theorem. Well, let's call it just the Hodge theorem. I'm not in the decomposition yet. That says the following. 1. These new spaces of harmonic P-forms are finite dimensional. Okay, the space is finite dimensional for any P between 0 and n. And more importantly, well, both things are important for us. The second part of the theorem is that, okay, I'm not gonna have a space here, so I'm gonna erase this part here. the second part is that you take the space of real forms, p differential forms, you can write this as a direct sum of the Laplacian of P and R. Okay, I didn't say this, but M is from the beginning compact, oriented, Riemannian, smooth manifold. All right. So, well, the input of this theorem is that the harmonic forms are a quotient of the space of all forms. Okay, but moreover, you can write this as since we already know how to write the Laplacian, this is d delta of A, P, and R plus, I'm gonna make more space here because I'm gonna need it. So this is this, which is also this plus delta V of, that should be the same, plus HP, but also this should be just D of AP minus 1. Using the adjoint properties, this should be this plus this right? So the space of P forms okay, let me see something else, which is an orthogonal. No, it is not only a direct sum decomposition, it's an orthogonal decomposition.
Excuse me, Jaime.
Mm-hmm.
Do you mean AP plus 1 on the previous line?
Yes.
Delta of AP plus 1?
Yes, you're right, sorry. Sorry. Yes. Thank you. So this is an orthogonal direct sum decomposition of the space of P forms, of differential P forms, all right? Consequently, I'm going to say more. Consequently, the Laplacian equation has a solution I'm going to call it again omega if and only if alpha is orthogonal. And by orthogonal, I mean orthogonal with respect to the inner product I defined at the beginning of this section. If and only alpha is orthogonal to the space of harmonic P forms. Okay. So this gives us a clue on how to solve the Laplacian equation. But it gives, actually, it gives us more. Before continuing with this, the proof is, as I said, the proof is very hard. I mean, both proofs, the proof of the regularity theorem and the proof of the Hodge theorem. I mean, well, it depends on how you see it, but you need a big deal of functional analysis to prove this. Uh, uh, the other thing I wanted to say, oh yes, I remember. This decomposition, now there is a trend in applied math to use things in some things called like topological data analysis and that stuff, which is very combinatorial. And they also have their Hodge theorem. What they mean by the Hodge theorem is this decomposition, but they use this decomposition in the setting of graphs, okay? Which is a very interesting topic, but I'm not gonna discuss that one here. It's a very applied thing that they use for some things on data analysis or whatever, okay? So they already know this, but in that special case, it is a statement in linear algebra, okay? So for us, what we can get as a consequence is the following theorem, is that, well, actually, I want to say something about the Hodge theorem. This one here, part 2 on the Hodge theorem is also called, I'm going to be very careful here. Some people also call this a Hodge decomposition of a P, right? But you should be careful when you use that word, because we are going to use the Hodge decomposition for another decomposition later, okay, in the complex word. So, but I have also heard that they use the word, the phrase for Hodge decomposition for this direct sum decomposition here. Okay, but just be careful when you read it. Okay, so, okay, what else I want to say? Okay, so another important theorem is that if you take bar omega, if this is the class of a, that should say closed P-form omega in the, now I'm gonna do what I promised. I'm gonna go back to the RAM groups. So if you take a class in the RAM cohomology group, of M, a compact oriented Riemannian manifold, then this class of omega contains a unique harmonic representative, which is very interesting. It is not very surprising that should be like that, but once we know the Hodge theorem, okay? So what I'm saying is that you can identify the RAM cohomology group with the space of p harmonic group forms, okay? I mean, every harmonic, closed harmonic form, of course, is in the RAM group, but the other way around is an import of this theorem. The proof uses of course, the Hodge theorem. And uses one thing called the Green operator, which is an operator G that goes from the space of real differential P forms to HP. Actually, you go to the orthogonal complement of that. And what this operator does is that, I'm not gonna talk about the proof, but perhaps some of you remember what this is. the green operator exists in another context. So actually what you do is you take alpha to omega, where nabla of omega is actually alpha minus I should say something here. Well, minus something here. Here you have some operator, let's call something applied to alpha. Let's call it H, right? And this operator is this is in HP orthogonal. Okay. So the important thing about the, I have to be very clear here. G commutes with all the operators introduced so far, with D, with delta, with nabla. So, and actually, with any linear operator that commutes with nabla, okay? So to finish now, for today, I'm gonna say there are several important consequences of the Hodge theorem. For instance, again, M compact orientable. I'm gonna drop the Riemannian assumption because smooth, because you know differentiable. Differentiable actually implies Riemannian. So we can drop that assumption. So you have a compact orientable smooth manifold. Then a direct consequence of the above identification of the space of smooth forms, of harmonic forms with the RAM cohomology group is that HPRM is finite dimension, right? Which doesn't seem like a great accomplishment, but it is because, okay, why is finite dimensional? Because we already know that these groups are finite dimensional. And we already know that this group is actually this one, and that's true, right? Perhaps you already knew that the RAM cohomology groups are singular cohomology. This is not as surprising, right? But if you don't know anything about topology, it is, in my opinion, it's like a something, right? So I'm going to stop this with this corollary. We're going to see some other two corollaries next time. So thank you. See you in the next.